Welcome everyone to the GISS Sea Level Rise seminar. We're very glad to have Dr. Dhrubajyoti Samanta, who is a senior research fellow at the Earth Observatory of Singapore in Nanyang Technological University and a research affiliate at CIRES at the University of Colorado. Dr. Samanta's research revolves around the intricate dynamics of ocean and climate and their representation in climate models, and includes study of sea level, monsoons, and tropical cyclones. He is a participant in the Clivar Pacific Region panel and the United Nations Ocean Decade Vision 2030, Group 5. Dr. Samanta conducted his postdoctoral research at the University of Aizu, Japan, and Texas A&M University in Qatar. He received his PhD from the Indian Institute of Technology, Kharagpur, and today he will be speaking on the role of anthropogenic forcings on historical sea level change in the Indo-Pacific warm pool. So welcome, Dr. Samanta. And
thank you, Patrick. And can you share the document?
yes, so I'll share a file in the chat that Dr. Samanta wanted to share with everyone. Okay.
Can you see my screen?
Yes, it's good for me. Okay,
Yes.
for others. Okay, good.
Okay, hello everyone. I am Dhruvo from Earth Observatory of Singapore at Nanyang Technological University, and thanks for joining today. Today, we will explore an important topic, the influence of anthropogenic forces on sea level change. And in our time together today, I will walk you through historical sea level changes in the Indo-Pacific warm pool region, examining how both the natural and anthropogenic factors have driven these changes. And my goal today is to give you insights into these influences at regional to local scale and provide a perspective on potential future scenarios if these trends continue. And as we dive in, I wanted to mention our recent publication in Earth Future, a product of international collaboration with leading climate scientists across the globe. This work highlights our commitment to understanding climate change impact on sea level and also reflects the importance of working across multiple disciplines. And before I discuss the attribution study, let me briefly introduce you to the Earth Observatory of Singapore, or EOS, where I am based. EOS is founded in 2008 and focuses on fundamental research on earthquakes, volcanic eruptions, tsunamis, and climate change in Southeast Asia to aim a safer and more sustainable society. The need for research institutes like EOS has become increasingly important for Singapore and Southeast Asia. The graphic highlights the array of hazards facing the region, from seismic to tsunami hazard to cyclones and rising sea levels. And many natural disasters here affect the large populations and are further compounded by climate change and sea level rise. To address these challenges, EOS covers key areas including climate, tectonics, volcano, and risks and society, and supported by dedicated centers for geohazard observation, remote sensing, community engagement, and corporate services. And this graphic shows the observational facility that EOS has throughout Singapore and focusing on multiple aspects of Earth system science research. A notable sea level initiative at NTU is the Southeast Asia Sea Level Program, or C2. Today's research focus is part of this large-scale project, which spans 5 key components. These include solid Earth contributions, global, regional, and local sea level, extreme sea level, future sea level projection, and flood impact projection. Since launching in late 2020, C2 project has achieved some impressive milestones. More than 50 publications, the involvement of over 40 researchers and students, more than 100 conference presentations, and creating important dataset for sea level research. EOS recently produced a briefing paper on sea level research, which Patrick has shared with you, providing a comprehensive overview of ongoing research activities in sea level studies in EOS in NTU. Our research comes at an important time when the rate of sea level rise is accelerating. Since the onset of satellite altimetry, the global mean sea level has risen by nearly 11 centimeters, which is a concerning trend. The graphic in front of you shows the global mean sea level rise from 1993 to 2023 satellite altimetry, and a quadratic model is also shown in dotted line. The shaded portion around the line plot indicates the uncertainty envelope of the global mean sea level record at the 1 sigma level, considering the uncertainty of altimetry observational systems. And the most concerning thing is that sea level rise rate almost doubled in recent decades compared to the 1993 to 2003 period. The acceleration is about 0.11 millimeter per year square, which is very much alarming. But only focusing the global mean sea level changes is not sufficient, as the regional diversity of sea level trends is considerable. This graphic in front of you illustrates how global averages mask significant regional variability, with some regions rising 3 times faster than the global average. The spatial variability is mainly due to the redistribution of heat under the influence of major climate oscillations, in particular the monsoon, El Nino Southern Oscillation, Indian Ocean Dipole, Pacific Decadal Oscillation, and the North Atlantic Oscillation. Regional sea level trends reflect that there is variation at different time scales, from large-scale structure in ocean basin to finer mesoscale structure in major current systems such as in Gulf Stream, Kuroshio, and the southern circumpolar current around Antarctica. And our study emphasizes the Indo-Pacific region, specifically the Indo-Pacific wormhole region, which is densely populated, that you can see from this graphic. The region has experienced sea level rise rates of up to 6.4 millimeter per year, almost twice the global average during 1993 to 2022. The graphic also highlights how vulnerable the coastal communities surrounding the Indo-Pacific wormhole region are, particularly low and middle income countries in Asia. The Indo-Pacific wormhole region is characterized by a permanent sea surface temperature above the 28 degrees centigrade and plays a critical role in various ocean atmospheric processes and that are essential for global water cycle. The Indo-Pacific wormhole region has expanded more than twofold during 1993 to 2022 relative to the 1900 to 1980 climatology. And this is due to increasingly dominant role of anthropogenic forcing in this region. It is therefore essential to attribute historical sea level changes in this region. Changes in sea level are driven by a large natural and anthropogenic factors, and understanding past climate forcing is therefore can guide us for future projections. Understanding past climate forcing is very much useful for sea level attribution. And this evolving science of climate change attribution improves our understanding of how the global climate system is changing and also aids discussion about responsibility and accountability for its effect. Prior research of attributing sea level changes to anthropogenic forcing predominantly focuses on global mean sea level. Let me give you some examples. Sokarska et al. Argued that ocean warming and global mean sea level are detectable over the historical period and attributable to the anthropogenic forcing. On a longer time scale, Dhrubajyoti et al. Evaluated the role of various natural and anthropogenic forcing on global mean sea level for the past 1,000 years based on a statistical model, and they argued that the past 200 years the sea level rise has been mostly due to the anthropogenic factors. Then Amich group published another interesting paper that used optimal fingerprinting approach to show that anthropogenic forcing are required to explain the magnitude of the observed global mean thermosteric sea level rise during 1957 to 2005. And then Sankej group published another interesting work. They provided a significant anthropogenic footprint on global mean sea level rise since 1900 by assessing the spectral properties, and they showed the slowly varying volumetric component and the rapidly changing atmospheric component while they showed the spectral properties. And then recently, Richter et al. Highlighted that anthropogenic influences are detectable on both global and basin scale sea level change. But sea level attribution on a regional to local scale is more challenging than on a global scale. This is because of varied expression of natural climate variability. Natural climate variability can emerge over multiple time scales without the influence of external forcing from anthropogenic forcing. And another challenge in attribution studies was the absence of the large ensemble simulation in earlier generation of climate models such as CMIP 3 and CMIP 5. And this is an issue to reduce the uncertainty due to internal variability in climate model simulation. But before I dive more detail into the attribution study, let me go through the components of the sea level so that we can have a recap on that. Sea level rise is very complex process involving a global, regional, and local scale. And then on the global scale, we see the thermal expansion, glacier, land water storage, and ice sheet are the major driver. And on a regional scale, the ocean circulation and density and the land water storage and the glacial isostatic adjustment are the driver. Whereas on the local scale, the tides, surges, wave activity are the driver on top of the mean sea level. And in today's lecture, I will be mostly focusing on the thermal expansion and ocean circulation density, that is also known as the ocean dynamic sea level component. So both of these terms together also known as the stereodynamic component. And let me show some basics on those aspects. This animation shows the thermosteric component. As you can see, when the temperature rises, the water occupies a greater volume so that sea level rises. And this is the thermosteric component. And we have seen in 20th century, the thermosteric sea level was the major driver of sea level change. On the regional scale, atmospheric and ocean dynamics drive the sea level by causing changes in ocean circulation pattern. For example, in Southeast Asia, the monsoon plays a critical role. Here you can see the southwesterly wind during the summer monsoon season causes sea level fall near Singapore Strait and Gulf of Thailand, whereas the northeasterly wind during the winter monsoon period causes sea level rise near the Singapore Strait and Gulf of Thailand. In fact, during the winter monsoon, the Gulf of Thailand experienced up to 40 centimeters of sea level rise relative to the summer monsoon period. The link between ocean atmospheric circulation and sea level change is very complex, but as the graphic shows, the stronger current moving toward coastline can elevate local sea level near coast. And this animation shows the relationship between sea level pressure uh, and the sea level change, where when we have the region with surface low pressure system as shown here, it effectively lifts the sea surface, causing a rise in sea level in that region. Conversely, when there is a surface high pressure, it pushes down the ocean surface, leading to a fall in sea level in that region. And this dynamic is also often known as the inverse barometric effect. This principle also plays a role in extreme weather events like cyclones. The objective of today's presentation and our research is twofold. First, to attribute historical sea level changes over Indo-Pacific wormhole region to anthropogenic and natural forcing, and second, to examine some background physical mechanisms for historical sea level change. For this research, we leverage the CMIP6 deduction and attribution model intercomparison project, or the DAMIP. One of the objective of DAMIP is to improve estimation of natural and anthropogenic forcing to observe global warming. And we selected 3 climate models based on the availability of at least 10 common ensemble members across different forcing simulations: CAN-ESM, CNRM, and IPSL model. And we use global mean thermosteric sea level, dynamic sea level from DAMIP simulation. 3 models successively produce many observed spatial patterns of the surface climate, interior ocean, and also the atmosphere. And this gives us the confidence to use those models. We specifically examined 4 experiments: historical aerosol, historical greenhouse gas, and then historical natural. You can see in the table, the historical simulation consists of all the forcing, such as time evolving greenhouse gas, black carbon, organic carbon, and ozone, stratospheric aerosol, solar irradiance, and land use. Whereas the aerosol only forcing simulation only considered the anthropogenic aerosol in the historical simulation. For the greenhouse gas forcing, it only considered the well-mixed greenhouse gas in the as a forcing. And for natural only simulation, it only considered the solar irradiance and the stratospheric aerosol. So you can see here, by comparing these experiment, we can isolate the different forcing on climate and also on the sea level changes. And in our study, we assume that linear additivity, that means the historical simulation can be expressed as the combination of aerosol forcing, greenhouse gas forcing, and the natural forcing. And this is also consistent with several earlier studies. We begin with the evolution of global thermosteric changes related to the 1950. Here the blue color plots indicate the aerosol only forcing, orange greenhouse gas, purple natural only forcing, and the black historical forcing. The historical simulation in all three models show that the global thermosteric sea level has risen up to 45 millimeter relative to the 1950. The rise is consistent with the observed global thermosteric sea level trend. And our results show that the rise in global thermosteric sea level is primarily caused by the greenhouse gas forcing. The greenhouse gas forcing shows that increased thermosteric sea level of nearly 80 millimeter from 1950 to 2014, whereas the aerosol force run act as a compensatory matter, such that the increase is reduced when considering their combined impact in the historical simulation. So you can see here that despite the spread in magnitude in greenhouse gas and aerosol forcing in different models, overall they agree that the rapid rise of thermosteric sea level is evident in recent decades. And we further examine the long-term dynamic sea level or DSL changes over the Indo-Pacific region for different forcing. Here, the change means the 1985 to 2014 minus the 1950 to 1979 average. And we started our analysis 1950 because of dominant anthropogenic influence on the global climate in the second half of the 20th century. And here the effect of seasonal, interannual, and decadal time scale is largely removed because we are considering a 30-year mean. And we ended in 2014 because the SIMIP6 simulation ends in 2014 for the historical simulation. And the results, what I am showing here is the ensemble mean, meaning this for CANISM, it's the mean of 30 ensemble members. And if you focus on the top panel, it's from aerosol forcing, you can see an overall DSL fall. Conversely, the greenhouse gas forcing causes a DSL rise in the next panel. And this DSL change suggests that aerosol and the greenhouse gas forcing are compensatory when average over this particular domain. And overall, if you see the historical simulation, it shows a DSL fall in the region except for the Western Indian Ocean, the Eastern Australian coast, and the around 20 degree north near the North Equatorial Current region, where DSL has risen in recent decades. And if you focus on the South China Sea, you can see a historical DSL fall up to 15 millimeter is noted. And in contrast, the Western Indian Ocean shows a rise of DSL up to 30 millimeter during a similar period. And even though I am showing the one CANISM model, but the other two models also show the similar pattern in the recent decade. And we also see a consistent positive Indian Ocean dipole-like pattern where you can see the Western Indian Ocean is positive and the Eastern Indian Ocean, the Indonesian Sumatra coast is negative. That means DSL fall. And the box here you can see in the historical plot is the region where I used the study for the time of emergence that I will get back to you later. And if we see the linear trend analysis of DSL during the 1950 and 2014 period, It shows a similar pattern of DSL change that I showed in the last slide, with greenhouse gas induced rising trend up to 0.8 millimeter per year over the Western Indian Ocean and up to 0.7 millimeter per year of DSL fall trend over the Eastern Indian Ocean. And a weak negative DSL trend is also observed over the Southeast Asian Sea, including the South China Sea. Meanwhile, the Eastern Pacific shows a greenhouse gas induced fall in the DSL trend in all three models. And as these results are derived from individual forcing that I explained earlier, the DSL changes are very likely the response to the specific forcing in the simulation. And despite spatial diversity in the magnitude of DSL changes, we can see that greenhouse gas was a major driver for historical sea level change. And we then attribute the sea level change to steric and manometric sea level changes. We can write the sea level elevation as the sum of three terms. First, the inverted barometer effect to the sea level, that's the zeta A. Then the second term is the manometric sea level, and the third term is the steric component, consisting the thermosteric and halosteric. And just to remind you again, here the steric change is related to ocean density if we assume the local mass of the ocean is constant. And then the manometric change is the non-steric component, and we can measure the manometric changes from the ocean bottom water pressure in the climate model simulation. As climate model simulation has no barystatic sources, the all bottom pressure changes occur due to local mass change within the global ocean. Now let's have a look at the thermosteric sea level changes. And note that here I am showing you the local thermosteric sea level changes after removing the global mean. In other words, this is the regional anomaly relative to the global mean. And here we focus on the changes in spatial pattern and magnitude from different forcing while identifying the causes of historical sea level changes. And you can see the thermosteric sea level anomaly is reduced in the region due to the aerosol forcing, except in the coastal and shallow regions of Southeast Asia and the North Equatorial Current region in the Pacific Ocean. Whereas the greenhouse gas forcing shows an increase in thermosteric anomaly in the Indian Ocean and a decrease in the Pacific Ocean and Southeast Asia. This compensatory impact of aerosol and greenhouse gas forcing in the region is evident, particularly if we see the shallow and coastal region. But overall, the thermosteric anomalies in the historical simulation are largely controlled by the pattern and magnitude of greenhouse gas forcing. The maximum historical anomaly in the thermosteric component due to greenhouse gas forcing is noted particularly over the Western Indian Ocean and east of Australia, which coincides with the highest DSL rise that I showed earlier. And the natural forcing on thermosteric sea level is relatively less in the region. And if we see the halosteric component in the next, it's the component associated with the regional salinity changes and due to the changes in local freshwater balance, such as precipitation, evaporation, and the river runoff. And you can see here the aerosol forcing drives negative anomalies in halosteric sea level in the northern tropical Pacific and Southeast Asian seas, while the other region shows that positive anomaly. And historical simulation shows the positive anomaly in halosteric component in the Western Pacific Ocean and the Western Indian Ocean. It is up to 60 millimeters from the greenhouse gas forcing. And similar to thermosteric anomaly, you can see the natural forcing induced halosteric anomaly are relatively much weaker in this region compared to greenhouse gas or the aerosol portion. And similar to the dynamic sea level pattern, you can also see here a positive IOD like east-west gradient in the Indian Ocean is reflected in the halosteric changes. And this is mostly from the greenhouse gas portion. And notably that regional thermosteric and halosteric sea level are of opposite sign relative to the global mean, meaning the historical rise in steric height over this region is also predominantly the result of the halosteric sea level change. Now, before going into the results of the manometric, let me explain you how this manometric sea level change occurs and how we can estimate that. The manometric sea level is very often used for the ocean warming detection, but for sea level studies, it sometimes overlooked. But an earlier study by Richter et al. Showed that the impact of self-mass loading due to the ocean bottom water pressure can increase the sea level by 10% of the total sea level in the Indo-Pacific region. The right side graphic shows the mechanisms how the shallow region gets higher sea level from the manometric component. Here you can see the deeper ocean get warmer, and then once it gets deeper, then there is a sea level gradient between open ocean and the shallower region, and thereby it creates a redistribution of seawater towards the shallower region from the deeper region. And then we can see a higher rise in sea level in the shallower region, that in the bottom graphic on the right side. And that results in the higher bottom water pressure and due to the self-mass loading. And this is indeed reflected in the climate model simulation that we studied. Here I am showing here similarly the changes in manometric sea level from different forcings. And you can see here the manometric sea level rise up to 20 millimeter over the Indo-Pacific warm pool from the aerosol forcing on the top panel, except for the coastal region and the shallow ocean in Southeast Asia. Whereas for the next panel, the greenhouse gas forcing reflects that opposite sign, but a similar pattern of manometric sea level change as of aerosol forcing. And the magnitude is up to 50 millimeter rise in shallow and coastal region. And if we see the natural forcing, it has an overall weak impact on its changes. But due to a strong but opposite impact of aerosol and greenhouse gas forcing, we can see the historical simulation shows around 5 meter of manometric sea level over deep ocean, but interestingly, up to 20 millimeter of rise over the shallow ocean and coastal region in the Southeast Asia and other Indo-Pacific regions. And this manometric sea level change in shallow water is significantly higher than the steric sea level changes that I explained earlier. Conversely, the steric sea level is more important in the deep water oceans, where it has more magnitude of changes compared to the manometric changes. Because the deeper region in ocean absorb more heat in a warming climate compared to the shallower ocean. As a result, the lack of balance between strong steric sea level gradient across the shelf and the geostrophy actually leads to the manometric sea level rise over the shallow region. So overall, if you see the Indo-Pacific warm pool region, the manometric sea level is very much important, and it is hugely driven by the greenhouse gas forcing. And indeed, if you compare the manometric changes with the bathymetry in this Indo-Pacific region, you can clearly see on the left side the shallow bathymetry in some Southeast Asia. It stands out very clearly, and it also clearly shows those are the regions Those are the hotspot regions for manometric sea level that I explained earlier and also can see on the right side graphic. And next, after investigating the patterns of changes from different components and the dynamic sea level, we investigate the evolution of anthropogenic component of dynamic sea level from sea level change and some physical driver in different regions, that the box that I mentioned earlier. And here, using the concept of time of emergence, we indicate when a single anthropogenic forcing drives the signal beyond the spread of variability from natural simulation. Meaning, if you focus on the left side, it shows the Western Indian Ocean, that IOD west box. Here it's showing the time evolution, the change in dynamic sea level compared to the 1850. And here we are saying it's a time of emergence when the historical signal separates from the spread that you can see in the shaded region. That's the spread of the natural variability. So when it separates from the spread, we call it as a time of emergence. And you can see that DSL has region over the Western Indian Ocean up to 35 millimeter by the end of 2014, while over the same period DSL has fallen over the Eastern Indian Ocean. And we note that anthropogenic signal and DSL in the Indo-Pacific region emerged first in the Western Indian Ocean. It's around 1940 that you can see on the graphic, and later in the Eastern Indian Ocean, it's around 1970. And when we compare the DSL changes, that means the evolution with sea level pressure and the zonal wind speed, we get an interesting feature. So here on the middle panel, I am showing the PSL, that means the sea level pressure. So in general, you can see that DSL rise is associated with the sea level pressure fall, and also on the lower panel, the weaker zonal wind speed. That means the westerly we can see, and also the opposite in this region. Whereas you can see in the Eastern Indian Ocean, we experience the DSL fall, and then we can see the sea level pressure rise. So as they are inversely related. And we can similarly connect the zonal wind speed changes in the Eastern Indian Ocean and also changes in the DSL changes. And when we see the South China Sea and the Western Pacific, they behave quite differently. For example, in the South China Sea, the greenhouse gas forcing impact on the evolution is relatively lower than the aerosol forcing. And that you can see here, the overall the historical changes in DSL is very less compared to the Indian Ocean, and mostly driven by the aerosol forcing. Whereas the Western Pacific Ocean, you can see the aerosol also has strong impact. Also the greenhouse gas also strong impact. So what we see in the historical, that's a balance between the aerosol and the greenhouse gas forcing. But when we see the sea level pressure and zonal speed, zonal wind speed in the South China Sea and the Western Pacific, it is the relationship between DSL change and the sea level pressure is not so clear what we have seen in the Indian Ocean. Rather, the relationship is very complicated, and we cannot easily attribute the DSL change to the sea level pressure change in South China Sea or the Western Pacific, because it could happen that the monsoon impact in this region is very strong. So that's why we cannot find such relationship in South China Sea and Southeast Asia region. But overall, what I discussed, that the time series analysis, through time series analysis, the time of emergence of the anthropogenic signal varies regionally, and indicating the regional to local scale dynamics has a strong control. And then I mentioned that anthropogenic impact on the dynamic sea level and other variable is significantly reduced by the aerosol forcing, indicating the historical dynamic sea level changes are driven by the balance between greenhouse gas and aerosol forcing. And we also found that the Western Pacific region shows a higher spread in natural forcing, which is consistent with substantial role of low frequency variability in the Western Pacific. And I also discussed that the time of emergence the anthropogenic of the anthropogenic signal on the sea level dynamic sea level change first emerged in the Western Indian Ocean, and then it emerges at the latest in the Eastern Indian Ocean. So far regarding the dynamic sea level, I have talked about the regional diversity in historical changes with the rise in the Western Indian Ocean, but fall in the South China Sea and Eastern Indian Ocean. And this regional variability in dynamic sea level may be due to variety of physical drivers. For example, the Western Indian Ocean may be rise may be consequence of the positive Indian Ocean dipole-like pattern that I mentioned earlier, and it can also be due to the rapid Western Indian Ocean warming. And we further tried to understand some of the physical mechanisms in terms of wind dynamics to explain these dynamic sea level changes in the historical period. And we study here the near surface wind pattern changes to examine the physical driver for the DSL changes. The greenhouse gas induced stronger easterly wind that you can see in this plot, particularly the greenhouse gas forcing over the Eastern Indian Ocean, causes a positive IOD-like pattern in the tropical Indian Ocean. And over the South China Sea, the historical wind pattern changes are not pronounced, whereas the weak westerlies in the central and eastern Pacific are also evident. And if you see the surface wind pattern over the Whirlpool region is mostly much weaker in the natural forcing compared to the greenhouse gas forcing. So overall, these results suggest that the historical changes in near surface wind pattern in this study in the study region is dominated by the greenhouse gas forcing. And this graphic similar to the last slide that I explained, but instead of zonal wind speed, wind stress curl is shown in the shaded variable. And we can see several changes in dynamic sea level in greenhouse gas forcing are associated with the wind stress curl. For example, the negative wind stress curl over the Western Indian Ocean and positive over Eastern Equatorial Pacific and north of the equator are associated with the DSL rise, and that I already explained earlier. So that means the wind stress curl affects sea level by imposing changes by Ekman dynamics. So when I see the negative wind stress curl, that creates a convergence of water and causes local sea level rise in the northern hemisphere. And moreover, we have seen in earlier studies, this discussed that wind stress curl also can trigger the westward propagating Rossby wave that can also cause sea level anomalies as they propagate. And these wind-induced changes in the tropical Indo-Pacific region strongly contribute to the regional characteristics of sea level changes. But our study is not perfect. It still has some limitation. And the three limitations that I would like to mention of our study are first, the absence of barystatic component. The SIGMP6 model lacks the barystatic component, limiting its accuracy. So in future, if we have better representation of the physical processes of polar climate, that can reduce uncertainty in climate model simulation. And then second, the resolution of the simulation. The model simulation that I used are of 1 degree resolution, but that may not be perfect for the coastal and the very local scale features. So we may need high resolution model in terms of the detection and attribution project to have better and the finer details. And then lastly, I also wanted to mention that all the climate models has more or less mean state biases, but how those biases can impact these changes that we have not studied, and that can be also possible future avenue to explore. And even though we have huge large ensemble, we substantially reduce the internal variability uncertainty, but we still cannot ignore the limitation due to these aspects that I explained just now. And our study has far-reaching implication. It provides a new insight into the anthropogenic influence on regional to local scale sea level changes, and it emphasizes the implication for regional to local scale shift in the future. And it also emphasizes the urgent need for emission reduction to ensure sustainable coastal communities, and thereby highlights the implication for coastal management strategies. So the take-home message for today's presentation is first, that we have used the large ensemble climate model simulation to attribute historical sea level changes in the Indo-Pacific whirlpool region. Second, the greenhouse gas forcing plays a dominant role in historical sea level changes, although the time of emergence varies depending on the location. And our study also highlights the important contribution of manometric sea level changes in coastal and shallow oceanic region, which is very often overlooked in sea level studies. And lastly, the tropical Indian Ocean dynamics have been crucial in driving historical sea level changes within the Indo-Pacific whirlpool region. And thank you for your attention.
Thanks very much, Dhruba. Do we have any questions?
Should we post questions in the chat, or can I just ask?
You can just ask. Yeah.
Oh, hi. Thank you for the presentation. If my question has to do with the El Nino system and the PDO, if those, if El Nino is varying, but its location, whether it's a Central Pacific event or Eastern Pacific event, how does that affect sea level in the Western Pacific whirlpool? Is there a way to isolate that from what you were doing?
Yeah, that's an interesting question. But as I said, like, we tried to understand the long-term changes. So when I showed the long-term changes, we have taken 30 years mean, so 30 years mean period. So we have not actually looked into the impact of ENSO, whether it's a CP or EP El Nino, how that impact, we have not explored that. So that, I think, a very interesting topic that we need to explore, but we have not seen that in our study.
So sorry, I'll ask again. So I was very interested in your early figure about the expansion of the Western Pacific whirlpool and how rapidly it's getting bigger. Is that simply based on sea surface temperature, or is that based on sea level anomaly, or both?
No, this expansion is defined based on the sea surface temperature. For example, the area of 28-degree isotherm, so that has expanded almost 2 times. So there are papers, so for example, the Roxy et al., they published in Nature in 2019. And also there are a couple of papers. Also in our study, we also shown that the area has expanded. So when I mean the expansion of whirlpool, it related to the sea surface temperature, but the sea level, in terms of sea level that I showed, even we see the sea level trend almost doubled compared to the global mean in that region. But that may not totally like one-to-one match of the Whirlpool region, but overall that region is experiencing almost double the sea level rise rate compared to the global mean.
Thank you.
Any other questions? I was kind of wondering if you were exploring the future changes in the region, and if you found anything related to that in the projection.
Yeah, our team in Earth Observatory of Singapore, they are doing some projection based on the tide gauge record extrapolating, and also I am working on the like dynamical downscaling of the sea level projection. But in terms of this attribution, we have not done so, but we are planning to do some like extrapolation of the historical period based on some statistical model, because as you know that climate model from the synopsis has no like no simulation for the attribution project for the future period. So the DAMIP simulation only available for the historical period.
I see.
So only what we can do, we can extrapolate based on some statistical model or technique. If we assume based on the different scenarios how this pattern can emerge in future, whether it's aerosol or greenhouse gas forcing. But yeah, that will be an interesting avenue to explore. We have not done.
Okay. Great. Any other questions?
I have one for Patrick. So you've recorded this.
Yes.
How can I access the recording?
Yeah, it will be posted on the GIS YouTube channel.
Oh, okay. Thank you.
Yeah. No, if you received the email, the link is usually in that email that I sent.
Oh, okay. Thank you.
Okay, great. Well, I guess we can stop there.
Thank you so much.
So, thanks again.
Yeah, thank you. I again just wanted to emphasize the briefing paper that Patrick earlier shared. So our group from Earth Observatory of Singapore and Professor Ben Horton, he is also working in the like leading that group. So we that produced that briefing paper summarizing all the sea level science that we are doing. I also have the Tanghua Lee. He is also one of my colleagues. He is attending now. He is expert in GIA. So we have a lot of expertise in the sea level group, and that briefing paper actually summarizing all the activities what we are doing, and I think that also provides an scope to like find out the scope for future collaboration.
Okay, good.
Thank you.
Okay.
Thank you.